Hello again, my fellow causal champions. I'm Anne Sinclair, and I'm your host today on Causal Discoveries. The gravity of today's episode is quite intense, as we attract an exemplary lineup of guests to continue our investigation into universal specificity, challenging the venerable theory of relativity. Be sure to subscribe to stay informed about new episodes in this series. Earlier in this series, Dan Harris made the bold claim that relativity is to the geocentric model as universal specificity is to the heliocentric model. He outlined 5 parallels between Kepler's validation of the heliocentric model and his own work on validating universal specificity over relativity, which we cover in this series. Last episode, Harris proved that specific work done causes time dilation using Mill's method. Check out these earlier episodes linked below for the full discussion. In this episode, we have 2 returning guests and a new one to help us complete the coverage of the first 3 parallels, revealing a new gravity model and an anomaly in general relativity that can only be resolved if its base assumption is false. I hope you enjoy this episode on Causal Discoveries. Please welcome our guests, who will help shed light on the nature of gravity: Dan Harris, Albert Einstein, and Sir Isaac Newton. Let's start at the beginning. Isaac, please explain what gravity is and how you discovered it.
Lady Sinclair, it would be my pleasure. So, gravity is an attractive force that draws all things together and diminishes with the increased distance according to the inverse squared law. It's a law where it's proportional to the inverse of the square. And so how do I know this? I had just discovered the natural laws of motion and gave proper conceptual meaning to the inertia for the first time. So an object remains at rest and or remains in uniform motion unless acted on by an outside force. And so when the sum of forces are balanced, so the forces in all directions of an object, this way, that way, that way, when it all sums to 0, right, the force is in equilibrium, there's no change in motion on the object. And then when the sum of forces are imbalanced or not 0, right, we say that there's some change in motion of the object. It accelerates proportional to its mass. So therefore, when looking out at the planetary motions using Kepler's model, right, where the sun is the center, I observed them accelerating towards the sun. The velocities were changing. Now, in some cases, the speed wasn't changing, but its direction was. And so, you've got your sun, you've got your planets, right? And the velocity is ever changing tangentially, right? So there's acceleration going on. So when looking at the motion of the moon, and its motion is accelerating towards the Earth, the Earth being the center and the moon be going around. And then when an apple falls, where does it fall? It goes to the Earth, and it starts at 0, and then it goes really fast later as further it falls. It accelerates towards the Earth. And so this change in motion is due to some sort of force. That's what my natural laws of motions are showing, unless, there has to be some strange force acting on all these objects, causing them to accelerate towards the center. And that's the force of gravitation, attracting them.
Fascinating. How did you determine that gravity is proportional to the masses involved and inversely proportional to their distance squared?
What a most interesting question, Anne. I love your curiosity, as it matches my own. See, why, I narrowed it down by the only means to do so, by a method that was later termed Mill's method. The same method Dan here used to discover the cause of kinetic time dilation in the previous episode. Links below. So I had to eliminate all other irrelevant factors by careful experimental design. I used pendulums as an example, and I changed the bobs out and measured the differences in the period, noticing that there were none. And I can rule out that the gravitational effect on attributes such as material of the object, its shape, its color, etc. So to which, altering these attributes had no effect on the gravitational force, made no difference in the outcome of the experiments. So they were not relevant to gravitational force. Objects fell at the same rate regardless of all these different changing of properties. The specific force was identical, meaning the actual force on the object, according to the F equals ma, is scaled by the masses because I eliminated everything else. So it was experiments such as these that allowed me to induce or deduce that the force of gravity is governed by the masses of the object involved in the inverse of the square. So there was some constant here. So now it's no longer a proportional sign. You can use this constant with this mass over r squared, and that's what the force of gravity equals. And this is the gravitational constant, right?
A most excellent achievement, Isaac. It's not common that someone integrates so many phenomena that were thought previously to be separate and distinct. I mean, the tides, planetary motion, and common experience of everyday things tending to fall towards Earth, all governed by gravity.
Oh, thank you, Anne.
Albert, please explain your understanding of gravity.
Of course, my dear, I'd be happy to. Gravity is a dynamic space-time process where space warps or bends, causing objects within it to appear to move, but they are actually stationary in the space-time, and it's the space-time that moves.
That's a significant departure from Newton's description. Can you explain why you believe this?
I considered what would happen if a painter fell from the side of a building. My happiest thought. Although not for the facts of the painter's ultimate demise. That's morbid.
Well then, why were you happy about it?
From his perspective, the ground and the building are accelerating upwards relative to him. This led to my equivalence principle, which states that within an isolated lab, all experimental results are the same, whether the lab is stationary on Earth or accelerating in empty space. Additionally, the results will also be the same when the lab is free-falling towards Earth compared to it floating in empty space. So you cannot distinguish between these situations. They are taken to be equivalents, free fall to floating, and sitting on Earth to accelerating in empty space. From that assumption of equivalence, I deduce my theory of general relativity.
Newton, did you want to comment on that?
No.
Are you sure? You seem bothered by something Albert said.
Well, Anne, if you must know, I'm bothered that this approach is considered science instead of pre-science. Albert here guesses a principle and then deduces all these consequences, which is not a valid method to discover natural laws.
What do you mean?
Well, I think it rather obvious that the method employed by Albert is rather childish, for the same reason Francis Bacon thought simple enumeration is childish and as an endeavor towards induction. Simply enumerating observations that align with the theory do not validate its base assumptions. So we don't know what the general principle is. And here, it's fair because, ignorance is the natural starting point. You must induce these understandings. But rather than employing Mill's method to discover the general principle, as I did, he instead guessed, then deduced consequences and saw if they matched the observations. Your audience ought to know at this point that this method is the same method employed by Ptolemy when developing the geocentric planetary model, which was predictive but causally senseless. Ptolemy assumed the Earth was stationary center of the universe, and then invented epicycles, this motion around nothing, to explain those observations based on this assumption. And space-time dynamics feels like the modern epicycles. So yes, it bothers me that I set the example for how to wrest natural laws from the universe, and this error has resulted back to Ptolemy's millennia-old methods of guessing. Not to mention, equivalent means the same in all essential respects. Are these two situations truly the same in all essential respects? Is it truly inessential that freefall results in change in relative motion between objects with different trajectories at different potentials, yet floating in empty space does not create any relative motion between any two objects? Let me show you what I mean. So, probably the easiest to see is observing that the moon, the earth, and planets are all in freefall. So you got the sun at the center, Earth traveling around, you got the moon traveling on the earth, and you got other planets, both inner and outer. And they're constantly in freefall. There's no external force from thrusters, they're just in freefall, but the relative motion are changing, okay? Yet, distant asteroids in vast empties of space maybe pass by each other in different directions, and barring no gravitational effects, their relative motions are constant. And even at the smallest of levels. So let's say you and your buddy are playing ball, okay? And at the same time, you decide to throw the ball in two different directions, okay? You throw it mostly horizontal, and your buddy throws it mostly vertical, okay? Now, we like to say that the potentials are approximately identical, just for simplicity, but they're not. Just slightly different altitudes produce different levels of acceleration, which means the relative motion between these two objects are changing imperceptibly as time goes on. This doesn't happen if you and your body are in deep space and one of you decide to throw the ball one direction and you decide to throw it in the other direction. It doesn't matter. The relative motion is in empty space is constant. So does restricting our vision to within the lab, so not being able to see outside, does restricting our vision within the lab, does this make this difference disappear? This seems like a potentially critical difference that is just ignored. I don't think an answer to why this difference can be ignored has ever been offered, nor do I believe an answer other than it can't be ignored is valid.
Wow, I see your point. Albert, can you be certain that general relativity is true?
Given the truthfulness of the equivalence principle, then yes. But I cannot be certain the principle itself is true.
Why not?
The principle is an assumption. While its consequences match observations, it may still be wrong, just as Ptolemy's model assumed that the Earth was fixed at the center of the universe was a wrong assumption, even though his model based on this assumption matched observations of his time. So Newton is correct in this regard. Just because it matches doesn't make it true. There might be some other observations yet to be made that might contradict in the future. So also, I'd be dishonest if I had not mentioned that the purely geometrical approach to gravity found in general relativity can also be found in Newton's universal laws of gravitation as well. That is to say, Newton's laws can be reformulated to become purely geometrical, to remove the force of gravity found in his laws. What this means to me is that general relativity may be in a similar situation, but in the reverse, where you reformulate it to a set of laws where gravity is a force. This possibility has troubled me later in life.
Newton, are you able to use Mill's method to refine your gravity model to account for observations only predicted by general relativity?
No, I cannot, as many of these concepts involved with these predictions, such as time dilation, came after my time. But I bet there is someone here of your time who can.
Ah, right. Dan, what's your take on all this?
First and foremost, Newton is correct. Gravity is a force, validated by Mill's method. However, Einstein's approach, while not a valid causal discovery method, is still useful. It made novel predictions and helped us anticipate observations that we wouldn't have otherwise.
How do we reconcile the observations predicted by general relativity with the view that gravity is a force?
Great question. We can integrate general relativity's predictions with gravity as a force using my causal discoveries that we covered so far. We have the newly discovered causes relating time dilation to the average effective speed of light. Since the speed of light is the rate of causality, as nothing happens faster than the speed of light, we derived this equation. So the dt prime over dt is equal to the c naught factor over c, which is equal to this relationship to specific energy. Okay, now this c naught term is the average effective speed of light relative to an object moving in the universal stationary frame, or the USF. This c term and the denominator is the average effective speed of light relative to an object stationary in the USF. Now what this causal relationship is telling us in this equation, that a moving object's rate of change is directly proportional to its speed of causality. As the same goes for a stationary object, rate of change is directly proportional to its speed of causality. Or just simply put, any object's rate of change is directly proportional to its speed of causality. So the average effective speed of light is truly the metronome of the universe, which keeps pace for all things. Now, time dilation is the slowing of change. It takes longer for things to happen. It's a slowing of motion. If it took 2 hours for a cup of coffee to reach room temperature, you send it off at high velocities, it takes longer than 2 hours. This relates directly to a reduction in the object's specific internal energy, that is, the specific energy within the object. So we have a specific energy model that we derived last time. So it's the total energy, which is 1/2 c squared, that's the total specific energy, is equal to this internal energy plus this specific kinetic energy, or the change in specific kinetic energy. So you have this relationship, which derives simply from this relationship. If you were to see the terms here and rearrange them, you would get this total energy equals, the total specific energy is equal to 1/2 c naught squared plus this change in specific kinetic energy. And so what this 1/2 c naught squared term is, it's the internal energy term, right? The internal specific energy term, and that's where that comes from. And so you have this relationship here now, where this equals 1/2 c naught squared, and because of this relationship, you have this c naught is equal to c over gamma k. That's like the Lorentz factor, okay? That's this inverse right here. And so you have this relationship where it's 1/2 c squared over gamma k squared, which means now you have a relationship with total energy to internal energy. So it's this total energy, this total energy term over gamma squared for the kinetic case. And so this that's the relationship between the specific internal energy and total energy, and this reminder here that this kinetic energy term is 1/2 velocity, that's supposed to be a u, squared. So that's the velocity in the stationary, relative to the stationary frame. Now, given this energy model, you can then relate time dilation to specific energy this way. So therefore, this time dilation equation, or this time dilation relationship, is again equal to c naught over c, which is then equal to, you can square both top and bottom, take the square root to capture equivalence, and then you multiply 1/2 to both sides, or on top and bottom. And therefore you get this energy relationship. So it's the square root of the specific internal energy to total energy. Or you can rewrite this whole thing in terms of time dilation squared. So you have this term squared, and then it's a relationship of internal energy to total energy. Okay. Now, on one end of the extreme, where there is no time dilation, right? That happens when the velocity relative to the USF, the universal stationary frame, approaches 0. Now, this implies that this kinetic energy term is equal to 0, as 1/2 0 squared is still 0. Now, from there, what that means is this gamma term. So the gamma term, which remember is the inverse here, is that approaches 1, as the 1 minus 0 over t to the negative 1/2, that equals 1. Which then implies that this C naught term is equal to C, because C over gamma, or C over 1, is equal to C, right? Now, this implies that the internal energy is equal to the total energy, because of the 1/2 C naught squared is equal to 1/2 C squared, because C naught is C. And so what you have here is that the max rate of change occurs when an object's motion is completely internal. There's no kinetic motion relative to the USF. So all of its motion is internal. There's a trade-off where you have the total amount of specific energy, and that motion can be translated into kinetic at the expense of internal, or you can stop kinetic and get complete internal motion. Now, on the other end of the extreme, let me erase this real quick. On the other extreme, where velocity approaches the speed of light. Now, this other end of the extreme, where velocity in the universal stationary frame approaches the speed of light, that's as fast as you can go, it's the speed limit. That implies that this kinetic energy, specific kinetic energy term, is equal to the total energy, right? Because it's 1/2 b squared, or in this case 1/2 c squared, right? Which implies that this gamma factor approaches infinity, because again, that's what you get when you plug in all the values to this inverse. Basically, you get 1 over et over et, negative 1/2, and this is 1 over 0, and then it becomes infinity. And then this implies that the internal specific energy is equal to 0, as the internal specific energy is the total energy over this gamma squared term, which is infinity squared, so that's 0. So this means all the internal motion stops. It's all kinetic, because the C naught factor, this average effective speed of light relative to the object, is now 0.
Wow, this is great. How does this relate to the gravitational case?
Now, in contrast to gravitation, we have time dilation gradients according to the Schwarzschild metric described in general relativity. Now, I'm going to erase this. Okay. So the time dilation equation, according to the Schwarzschild metric, is this dt prime term over dt, and that is equal to 1 minus this 2gm over r over c squared, and that is square rooted, right? Now, this gm over r term is actually specific work done by gravity as the object moves from infinity to the distance r away from the object. So that is represented like this. And then you can simplify this into a change in potential energy. And we already know that this 2 over c squared is actually supposed to be 1/2 c squared. So we'll cancel this and put it down here. And we know that that is total energy. So this now relates to energy as follows, just like in the kinetic case. So this is specific potential energy, the change of, as the object approaches from infinity to r. And then this is your total energy, and then this is your half root. Now, what this means is as the object gets closer to the gravitational source, or as the r term here gets smaller, it takes longer for change to occur. Time dilation happens. Now, we know this occurs, and we've observed this and measured this many times, from clocks on different levels of building to GPS timing to account for phenomena. So in the GPS case, this is critical. So you have like Earth, right? And you have your location, which you don't know. That's what you're trying to figure out, okay? And you've got some satellites here at 2 different locations, let's say in this 2-dimensional case. And you know, you can measure the time that this message was sent and the time it arrived. And so you have the time. So timing is very important. Timing gives you, since you know the speed of light, gives you some radius at which that message could have arrived at numerous different locations. And so you have, in this particular case around this satellite, you don't know exactly where you are on this radius. You just know that it arrived from the satellite at a specific time. And then that's why you need 2 satellites. So you got the second satellite here with this other radius, and you know, you can eliminate the factor not in space, but where it intersects here, that's where you're located on Earth. And timing is very precise. If you didn't account for general relativity's time dilation observations, then your GPS location will be off significantly, and it gets worse throughout the day. And so it takes longer because of this time difference for actions to complete closer to gravitational sources than it would take for the same objects much further away from any gravitational influence. So as with the kinetic case, this relates directly to an average effective speed of light, as the speed of light is the rate of causality. So if we were to relate this to the speed of light over c, and again that equals this term over here. So the effect of this was confirmed where the speed of light is reducing by the Shapiro light delay test. In this test, tested a signal from Earth, and the idea was to send this signal over to Mercury, which is smaller, and then let's say the sun is in the way, right? It was by design, the sun was in the way, it's really big. Now, as the light went from Earth to Mercury and back, if there were no time delay, you would have an expectation of a return time. And then accounting for time delay, you would have a delay because the speed of light in this region, right here, close to the sun, was slowing down compared to when it was further away from the sun. And this has been observed and confirmed through experimentation, that it does take longer because of the light speed reduction close to the sun. Now the C naught term is the average effective speed of light relative to an object under gravitational influence, measured in a coordinate frame far away from the influence. Now if you're here, because you're time dilated or contracted, you don't notice, you wouldn't measure a difference in the speed of the light. But if you're further away, like if you're way away in space and you're measuring how fast that light is moving, it would be slower than the light is moving near you. That's what I mean by measured from the coordinate frame, a coordinate frame really far away. Now the C term is the average effective speed of light relative to an object far away from the gravitational influence. Now, what this causal relationship captured by this equation is saying is that the object's rate of change is directly proportional to its speed of causality, just as before in the kinetic case. So, and just as before, time dilation is the slowing of change in motion. And this gravitational time dilation, just like in the kinetic case, relates directly to a reduction in an object's specific internal energy, which again is the specific energy within the object. So let me erase this to get more room. Okay, so we have a different energy model. So we have this total energy is equal to this internal energy plus this change in potential energy. This is all specific, right? So total specific energy, internal specific energy, and change in specific potential energy. Now this follows out directly again from this equation, from relating these two things. Okay, so if you were to rewrite this, what this amounts to is the total energy is equal to this 1/2 C0 squared plus this change in specific potential energy. So that's what, if you rewrite this, that you get this, and then this term here is the specific internal energy term. Okay. Now, so what that means is that the specific internal energy term is equal to 1/2 C0 squared, where again C0 is equal to C over gamma P. So relating gamma P is the inverse of this, and so the change in specific potential energy is this GM over R term. And therefore, we're able to relate time dilation to energy in the gravitational case as follows. So you have this factor is equal to C0 over C as before, which is equal to the root of these things squared, right? Didn't change any values here, just square rooted to square. And then we're adding 1/2 to both terms, then consolidating. It's equal to the square root of this internal energy over this total energy, right? And you could rewrite this such that your time dilation squareds or time dilation terms are squared, and then it's just equal to this internal energy over this total energy. So internal over total. Now, on one end of the extreme, where time dilation is non-existent because you're infinitely far away, your R term approaches infinity. And this implies that the change that the gravitational field made in the potential energy, the amount of work it's done, is 0. And that's because you have this GM over R, which is infinity, right? So it turns to 0, which implies that this gamma P term is equal to 1, because you have this 1 minus 0 over this total, and that equals 1. Now this implies this gamma term, because C0 is related to C with gamma, is equal to C. So the C0 is C, because your C over gamma, which is 1, is C. Now that implies that the internal energy is equal to the total energy. The internal specific energy is equal to the total energy, which again is 1/2 C0 squared over 1/2 C squared, because your C0 and C terms are equal, which means your rate of change is maximum when R is infinity. Now, on the other end of the extreme, we're going to erase this so I can have more room. So on the other end of the extreme, where your R term is approaching the Schwarzschild radius, and that's your GM over this total energy. That's the radius at which light can escape, right? That's your event horizon radius. That implies that the amount of change in potential energy that caused by the gravitation is equal to the total energy, which is 1/2 C squared. Okay. And this implies that your gamma P factor is equal to approaches infinity, because you have this 1 minus this ET over T, 1/2 inverse, and that's in 1/0. Okay. And that implies that this internal specific energy is equal to 0 because your total energy over gamma squared, which is infinity squared for gamma p, is equal to 0. Now, that's basically everything stops whenever you reach an event horizon. Light, the speed of light, it approaches 0. The internal specific energy of any object approaches 0. Things stop changing. All right. Now, there is one key difference in the specific internal energy reduction for gravitation than for the kinetic case. Now, it's a function of distance, so its reduction is not static with respect to distance. As in the case with the steady state kinetic case, it forms a gradient, which is a function of distance for this gravitational case. So I'm going to get some more room here. Now, so the gradient of this internal energy within objects, a specific internal energy, for the gravitational case, is a change. Its fancy term is a nebula or del. It just means gradient. You're taking the derivative with respect to distance of some kind. And so in this case, we have the change of internal energy over r versus the kinetic case, which is the change in internal energy over s being the distance it travels as a function of time. Now, this equals 0 for the kinetic case because we're not accelerating. And this doesn't equal 0 because of this r term up here in the gravitational case. Energy gradients represent an imbalance of energy, right? So you have some internal energy higher than others. So an object under gravitational influence has more specific internal energy on one side than the other. And this negative gradient causes a force. So more specifically to this case, the negative specific energy gradient causes a specific force, which is why everything falls at the same rate under gravity. So we're going to go ahead and write this relationship and how you would derive it. So a negative gradient, right, is equal to the negative of this derivative with respect to r, and EI has a relationship to gamma squared, right? So it's equal to total energy over gamma squared for this potential dr. Now we're going to write this term out explicitly. So that's equal to negative change of 1 minus gm over r over this et term, and et, right, over dr. Now you can carry the terms and then cancel, so this et term can distribute and cancel, and the drs, this derivative can distribute, and so what you end up getting is this det minus d over dr over dgm over r dr, right? And this whole thing equals negative gm over r squared, or the Newtonian gravitational specific force. And so Newton found that the change in velocity for distant objects like planets was caused by a force of gravity acting at a distance. And now I have discovered the local mechanism responsible for that force, the speed of light gradient that exists around all objects, affecting the specific internal energy of all objects under the gravitational influence. And so this integrates together the observations predicted by general relativity with gravity being a force. And so this extends the natural law of gravity to a natural law of internal specific force. And there you have it.
Superb! Well done, Dan. I love this approach and the framework you laid out. Space-time dynamics seemed too abstract and removed from the real things any of us interact with. Empty space, which we can't see, touch, smell, hear, or otherwise affect directly, was somehow supposed to be responsible for physical motion. I like that with specificity, the specific force of gravity can be explained as a negative specific energy gradient within objects. It's so simple, clear-cut, and I can mentally see the mechanisms at work as time dilation gradients correspond to energy gradient, which corresponds to the motion of particles within my feet moving ever so slightly slower than the motion of particles within my head, which forces the system, that is my body, downwards toward Earth. Wait a second. Al, what implications do gravitational specific internal energy gradients have for the equivalence principle?
A specific internal energy gradient existing within objects near gravity, but not within objects in empty space, is another aspect we could ignore to maintain equivalence, but as you might have guessed, to ignore this is beyond reason. Incorporating this physical law breaks the equivalence I had assumed to be true. Yeah, Dan's discovery of universal specificity offers the physical counterpart to the geometric model of general relativity. And I very much look forward to seeing more implications of this work.
As do I, Albert, but that will have to wait for further episodes in the series. Thank you all for joining us. Thank you, Isaac, for showing us the method of causal discovery in such a grand fashion, uniting many phenomena. Thank you, Einstein, for creating such a grand model to predict observations Newton's model couldn't. And thank you, Dan, for giving those observations an easy-to-understand causal basis.
The most welcome, man.
In summary, we see that with universal specificity, it leads to new physical laws causally linking time dilation, specific internal energy, and gravity. It revealed the equivalence principle as an assumption, ignoring key facts such as the difference between relative motion for a free-falling object and an object floating through empty space. The addition of the fact that specific internal energy gradients exist within objects near gravitational sources but not empty space is a new difference that cannot be ignored, breaking the equivalence principle. Universal specificity ultimately reconnects to Newton's laws of motion, such that relative change in motion is due to a force. We've now completely covered parallels 1 through 3 between Kepler's work on planetary motion and Harris's work on universal specificity. We have more in store for you on the 4th parallel, and that's where we'll pick up next time, further integrating gravitational and kinetic time dilation into total time dilation and deriving its cause. Until then, you can review the status of this series production by referencing the WordPress link below, which captures the draft outline of this video series and the progress of its development. Don't forget to like, subscribe, and share if you enjoyed this video, and please add your comments and questions below. We want to hear from you. I'm Anne Sinclair, and until next time, enjoy making causal discoveries.
Let's go. Yo. I'm like an addict, do I gotta have it. I ain't even playing, got a really bad habit. If it moves, gotta grab it, fuse like a magnet. Lose, won't have it till I'm doomed in a casket. I ain't playing, got a weird mind. If you work 8 hours, I'ma work 9. If the shit tastes sour, you should taste mine. I'ma stay in power for a long time. Get up, nah, I ain't a quitter. Toss me the ball, I'm a really big hitter. Big picture, I'm a straight killer. Rising the song to the highest bidder. Got juice, got gas, I'ma move fast. New shoes, new tracks, like who's that? I'm new, come back, better than last. Yeah, it's a new me, never gonna look back. I'm never gonna look back. Cause damn, I was built to last. You move slow and I move fast.